I have that from time to time myself. But let's turn on our, those of you that have it, I know there's one or two people that have emailed me that said they didn't have a video camera, right, or a mic. I get it. But those of you that do, please turn yours on. And I know there's some of you that never turn those on. But whatever. Questions before we get going? So, questions before we get going? Okay. So today what we're going to cover is we will cover just briefly, less than 5 minutes, of what we've learned in the past that we need to know for the future. And after that, we're going to jump right into this chi-square where I left off on the last class. But I just want to tell you guys, like, tomorrow is D-Day. The day where I said that it's going to make sense, where everything's going to turn around on a dime, and you're going to understand, oh, this is why we're taking stat. That day be tomorrow. So just get prepared. Bring yourself a little bit of ice cream or cookies or something, because we're going to go through it. You're going to get excited. Oh my God, this is great. But then I'm going to start talking, and your heads are going to start pounding. And then you're going to go, oh my God, how are we ever going to learn how to put this together? And we will. Watch. Okay. Any questions? So I graded problem set 1 and 2. Problem set 3 is not due yet, so I didn't grade it. The midterms, I got through about 3/4 of them, but I haven't posted any of the grades until I'm done with all of them. Looks pretty good. Average grade so far about a B. So we're not that far off. I mean, we're actually doing pretty good shape. I know that there's a few of the recordings, and for some reason, I'm not sure because the size is so big, but I keep on trying to upload it. It keeps on bumping me off. And so I'm trying to figure out a workaround from that. And I may just post them on YouTube and then just put a link there. That way we're able to get to them, because that's easier to do. Okay? So if I post them on YouTube, quick fix. But to encode them and then bring them to Lalima takes a while. Okay. Any questions on anything so far? So today I should show you how to run a chi-square, do the chi-square PowerPoint presentation, explain a little bit about what the chi-square is actually doing and why it's important. Okay. So the first thing that we learned about was something called a population. Whenever you're studying stuff, it's always best to study the entire population. Why? Because you get the accurate answer, right? When you study the entire population, come on, where's my screen? There we go. You get the accurate answer. So if we wanted to find out the average income for somebody in the United States, what we would do is we would test every single person in the United States, from somebody just born all the way to somebody right on their deathbed. And we would find out how much income they have. And then based off of that, we can just divide it by the entire population. If that average income is like $80,000, if you make $79,999, it's below average. If you make $80,001, it's above average. But average is exactly $80,000. Then we'd be able to have that number. But for some reason, because people are constantly being hired, fired, laid off, companies going out of business, just all kinds of stuff going on right now, that number that we get is only good until one person gets a new job, or somebody gets fired or laid off, or a company shuts down, right? If somebody gets a raise, that number's no good. If somebody gets a cutback, that number's no good. If somebody's in sales, they have big sales or small sales, and it doesn't fit with that number's no good. And so we have to be careful, because often, you know, when you measure inflation, it's really not, that number's, you know, probably not accurate for a long time. So what we've learned how to do, instead of measuring the entire population, just do a sample. Because sometimes a sample will give you a number that's close. And matter of fact, when we use a confidence interval, you can say, wait a minute, even though the population, that number for the population could change that parameter, but as long as we have this confidence interval, we could estimate forever what that parameter should be. And so sometimes using the sample is actually better than the entire population. Just saying. And so after that, we looked at data, we broke it to categorical and numerical. Why is that important? Because for categorical data, there are certain charts and graphs, and for numerical data, there are certain charts and graphs. Right now, what we're looking at with categorical, we have two tests that we've learned about. One's called the z-test, and one's called the chi-square. We're learning about the chi-square right now. What's the difference between the z-test and the chi-square? This gives us more than two variables, but we can also add on some other stuff as well. That's what makes them different. Why they start? Hey, can we compare two things? Yeah. And then somebody's like, can we compare more? And so when you're looking at these, you're like, what's the big deal? What's the big difference? Two things, more than two. Then we went to numerical, and with numerical, we have the t-test, and we have ANOVA. What's the difference between the t-test and the ANOVA? The t-test is variables. The ANOVA is more than variables. Okay? That's a huge difference. Looking at these, they have different assumptions and that type of stuff. We'll talk about those in just a second. But I just want to make sure that there's a reason why we need to know if it's categorical or numerical data. Because we have different tests and we have different charts and graphs we can make. So it's kind of important. Then we looked at descriptive and inferential. Descriptive, just simply descriptive statistics, the shape of the data, central tendency, variability. If we're looking at a certain drink or something, perhaps we're looking at a cup of coffee, and we're looking at different coffee makes, like maybe Blue Mountain, maybe we're looking at French roast, and maybe we're looking at Kona coffee, and we want to find out, hey, wait a minute, which one has more caffeine? We can do that. We can measure that. The descriptive statistics, maybe say Kona coffee has this much caffeine. The Blue Mountain has this much caffeine, and perhaps that French roast has this amount of caffeine. So we can look at those means, and then, hopefully run a test or something with it, but the descriptive statistics would just give us a raw number. If we wanted to infer something, then we would test with it. And we would test to see if one number is above another, and if it is, how can we test 3 different coffees, and we're looking at numbers, we'd use that ANOVA. If it was 2 coffees, we would use that t-test. And the inferential would actually infer, wait a minute, well, because the Kona coffee has more caffeine, hypothetically, caffeine gives you more energy. So if you wanted more energy, you would drink the cup of coffee. We'd be able to infer that based off of the data. Okay, so inferential is kind of inferring things based off of data. Descriptive statistics is kind of giving us the data on things. After that, we started looking at data. We broke it into the shape, central tendency, and variability. With the shape, we have skewness and kurtosis. What that tells us is our shape normal? Does it represent the normal population, what we would normally find in data? 2, do we have outliers? Right? And 3, is our probabilities good? If it's not normally distributed, then our probabilities are no good. And guess what? For the t-test and the ANOVA, we want to make sure our data is normal. And so to ensure the accuracy of these tests, we look at the shape of our data, right? And to make sure that this test is testing what we would normally find, we also want to look at the shape of the data as well, right? Central tendency tells us the average. And so typically when we're running things, we're comparing means against each other. And so we want to make sure that we're, so central tendency, the mean is the mathematical average. So we need those means in order to test these things anyway. Okay. Variability lets us know how much something varies from the mean, from the mathematical average. And so the standard deviation is the average amount that something varies from the mean. The coefficient of variation is the percentage that something varies from its own mean. And the IQ is that middle 50%. Okay? You with me so far? And so when we look at these, one of the assumptions for the ANOVA is that we're measuring things that vary about the same, that have the same consistency. Because we want to make sure that one is consistently higher. So one of the assumptions for the ANOVA is deviations are okay. You guys with me so far? The next thing that we looked at was we made this bell-shaped curve. And after that, we put in a mean, and we put in standard deviations. 1, 2, 3, 2, 3. And from that, we were able to then add in probability. And then we were able to add in empirical rules. And then from that, we're actually able to do normal probability. Why do we call it normal probability? A bell-shaped curve is called a normal curve. And we're using probability based off of a bell-shaped curve. And so what have we done? We have solved, based off of standard deviations, what's the probability of any number. So all we have to do is to find out how many standard deviations something is above or below the mean, and that would give us a probability. And so what we do is we solve for something called a z-score. And that z-score would give us a number that we'll be able to figure out the probability. Above that, below that, or in between 2 points. When we solve what's the probability that something's in between 2 points, we can then say how confident we are that somebody jumped from 2 to 10 feet. Now, when I'm saying like from 2 to 10, that's an interval. That's a grouping of numbers. How confident am I that somebody would jump from 2 to 10? 95%. So now that I'm able to tell you how confident I am that something's in between an interval, we call that a confidence interval. Okay? A confidence interval allows us to predict what, based off of a population, we have a parameter, so we can predict what a parameter is based off of this, and say how confident we are that the parameter is in there. So now that we're able to do that, we can start testing things, all kinds of stuff, which is kind of neat. And we can see, is something in here or is it outside? Now the problem that we run into is that typically the stuff that we test, the stuff's dynamic. There's a word dynamic. It's not constant. It's kind of all over the place. You look at stock, 1 minute it's at $8, next minute it's at $7.50, it's at $9.10, it's all over the place. But what's the average of it, right? And so sometimes when things are kind of all over the place, you need to be able to say, hey, just because one number is higher than another one at this given point doesn't mean that it's significantly higher. You have a stock that normally trades at $6 and that's at $6.50. Is that significantly higher? Just normal variability throughout the day. It goes anywhere from like $10 to $2. And so when it's at 6 or 8 or whatever, it's just normal variation. It's going to go up and back down, and we don't worry about that because it's not any different. When it gets above 10, it's significantly different than it normally is. We got something there. When it gets below 2, it's significantly different than what it normally is. So anything in here is considered the same. Anything outside is statistically significantly different. So then we can start testing things to see things that are different or not. So what we like to do is we like to establish what we're going to test. Right? You just don't test things. You want to, okay, what am I going to test? Right? So imagine if I thought, hey, wait a minute. Looking at people, and right now we have something taking place right now. So we have our null and our alternative. The null means that there's no difference. The alternative means that there's difference. Right? Whatever it is. And so all the tests that we're testing, every single test, the z-test, the chi-square, the ANOVA, and the z-test, all of those basically just tell you if two things are different or not. Right? Correlations tell you if they're the same. These tests are telling us, hey, are these things different? And that's what we're trying to find out. So now we're able to test things that are all over the place and see, hey, is one consistently higher than another one? Does this product sell more? Is this marketing plan better? Is this safety plan better? Right? Does this machine really put out more stuff than the other one? We can test this, and that's what we're trying to do here. So imagine right now we have something taking place. It's called COVID. And imagine if we were to notice like patterns. And so sometimes patterns in the data tell you something. Is anybody in that class an athlete or played football in the past? Can somebody chime in and say, that was me? Anyone play football? Baseball, basketball, anything? Baseball, volleyball. Okay. Got Carson, you play any sports?
Yeah, I did.
Which sport?
I played football.
Okay. So let me ask you a question. So you're playing defense, and you have a quarterback, and he's in the shotgun position. He's in the back, right? He's in the shotgun. They have no running backs in the backfield. That pattern tells you the quarterback's going to do what?
Gonna pass it.
It's going to pass. That pattern tells you it's going to pass. You're playing football, and it's on the goal line, and it's 3rd and 3 inches. The receivers get pulled in. They have 3 running backs in the back. It's not even the normal quarterback. They have some quarterback that they put in that's like 6'6", 310 pounds. And that would tell you that they're going to do what, Carson? Help me here.
They're gonna run it.
And so a lot of times, the patterns of the data will actually tell you what's taking place. And so sometimes you look at these patterns, and you can say, wait a minute, this is going to happen. Based off of this pattern, that pattern, this is a probability that that will take place based off of how these things are lining up. And that's what we're kind of looking at, right? The probability that an event will take place, the probability that they're going to pass, based off of these variables, we would say 99% probability that they're not running it. Unless it's a quarterback running it, but it'd be pretty stupid to be in the shotgun if he's going to do that. But it would tell you the probabilities of these events, okay? So when we're testing things, all we're trying to find out is there a difference between whatever things we're testing. Is one different than the other one? Greater or less than? That's it. Or not equal to. And so imagine if I was trying to look at, we have this thing called COVID right now. And like, is there a DNA component to it? I don't know. Like, imagine somebody comes out with something crazy thinking, hey, wait a minute. I think people that have A blood type, O blood type, and AB blood type would all have the same probability of getting COVID. Did I leave one out? That's it, right? And right here you put not all means are equal. There's a probability that one blood type actually gets COVID statistically significantly higher than the rest. Wouldn't that be crazy if that took place? And you start thinking, oh, wait a minute, maybe there's a problem here. Well, guess what? Somebody say what? What? Come on, you got to do it. We got to do it. Guess what? Somebody say it. Somebody say it. Come on, Edna.
What?
There we go. Let me share the screen with you. And on my side, it looks blank. Okay, here we go. We're going to exit out of the sign up for updates thing. Can you guys see my screen? Is there a yes or no? No? Can you see the screen, Edna? Okay.
I think it's like loading on my end. It's just kind of black and it says, oh. Yeah, now I can see it.
Okay. Okay, we can see it now? Okay. Ouch. My screen went.
So you gotta go up there and hit exit full screen.
Screen sharing paused. Why is that?
Oh, did it pause it?
You jinxed me here, Edna. And that. Okay, I got to do this again. Share screen. Come on. Let me do this again. Well, guess what? Go ahead.
What?
Oh, there we go. Okay, can we see it now? Elisa, do we see it? I'm not asking Edna because she always tells me no.
No, I don't see it either. But it's same as, oh, here we go. It's loaded now.
Here we go. Come on, man. You guys. Okay, so do we see this right here where it says patients with blood type A have higher rates of COVID? Well, you know what's interesting is they started looking at all the people with COVID, and guess what they ran? Somebody help me here. Do we see this right here? Where it says study was conducted comparing blood type groups distribution of 2,173 patients with COVID-19 compared to SARS. A test for 3 hospitals, Wuhan. What test did they run? Somebody help me there. A one-way ANOVA. And so what they did was they ran a one-way ANOVA, and they wanted to find out if blood type was significant as far as people getting this disease. And you know what they found out? Blood type A, if you have blood type A, you are significantly higher probability of catching this disease than blood type O. And the funny thing is when they looked at the populations in the cities, in one population they had, I forget what it was, like 13,000 people with higher amount. So they had higher amounts of people with blood type O than they did with blood type A, but the blood type A got more of the disease. So they found out that people with blood type A have a 50% higher probability, yeah, it's huge, of catching the disease. And there's another study that shows that people that have blood type B have a significantly higher probability of getting very sick and actually dying with COVID than any other blood type. So they actually have a DNA component. But the interesting thing that I wanted to show you is that the test that they use is actually ANOVA. We know how to run that. And so with the ANOVA, what it's telling us is we're looking at this. Guess what? Blood type A, if you have blood type A, you have a statistically significantly higher probability, and it's a 99.9% probability of catching it compared to the other blood types. Blood type O, statistically significantly lower probability of catching it. Statistically significant. And the other ones like A, B, and B are in here, which is kind of interesting. And they've done other studies, but this is all based off ANOVA. This is what we're learning, ANOVA. Do they just use it for like business? No, they use it for all kinds of stuff. Just kind of want to throw that out there for you guys to see, like they're actually using this stuff right now. And you could actually read these results and come up with, hey, wait a minute, I understand this. I understand what they're testing, what's taking place, and is it significant or not? And so we're actually finding some significant evidence. Now let's go to our chi-square. Why is this important? Okay. So with our chi-square, it's categorical, but it allows us to test things. Like, and I'm going to throw something out at you, right? Boom. So here we're looking at a couple different hotels: Hilton Hawaiian, Ohana, and Holiday Inn. Right now, all of them are closed. But imagine if they were open, as they normally are. And we're looking at what the drivers are for people to go there, right? And I need to start off simple before I start adding stuff to things, so you're able to build around it and understand it. So I'm going to start off simple. So we're looking at the reasons why people stay at these hotels. Is one reason possibly is price, another reason location, availability, and other. Now we're looking at that for Hilton, Ohana, and Holiday Inn. So when we look at Hilton, how many people stay there for the price? Not very many. And the people that stay there for the price stay there because it's more expensive, not because it's cheaper. Right? Sometimes people buy a Philippe Patek watch because this is Apple, but they buy a Philippe Patek watch because it's more expensive. Like the cheap one is about 80,000, one of the cheapest ones. The most expensive, $3 or $4 million, but some of the cheap ones are about 80 grand. People buy it not because it looks the best, but because it has a higher price, right? How many people go to Hilton because of the location? Large number. Availability? Not so much. Other? Ohana, the price, that's a driver there. Location? A couple blocks back off the beach, they don't care. Hilton Hawaiian, you just walk out of your hotel room right onto the beach, right? Kick the hose off the beach and then go swimming, right? But Ohana, we got to walk a couple blocks. They don't care because the price is good. Availability, kind of important. Other, Holiday Inn. How many people stay there because of the price? That is the driver. That's the driver. Location, got to walk 5 blocks. Got to take an Uber there to the beach, right? We're interested in price. Availability. Now, why is the availability kind of important? We'll get to that in the next example. And here's other. Now let's change it to another product. Let's change these to cell phones. And then I'll kind of explain on these a little bit more. So we're looking at these cell phones. We have the Apple, Samsung, and the Track phone from Walmart. How many people buy the Apple because it's cheaper or because of the price? Not a lot, but some. I mean, there are more expensive phones. There's some in Vietnam that are like 20 grand or 28,000, sorry, that are solid gold. You buy that because of the look. It gets horrible reception. It looks horrible. But people buy it because they like it because of the price. But here, how many people buy Apple because of the price? Very low. But what you do like, I have an Apple phone. I want to buy one. I just go to the mall, pick up an Apple phone, walk into the store after they check your temperature, just about tase you, whatever. When I walk into the store, I pick up a phone. Something goes wrong with my phone. I walk out. The next day, I go to make a phone call, and my phone's not working. I go to the Geek Squad, and I'm just like, dude, phone broken, fix it. I'm going to go get a latte, right? And they fix it. I like that. The Geek Squad, no, they're not the Geek Squad. That's the other people. They're the geniuses, right? So, okay, genius, fix this, right? Then I go get my latte. I like that. I like that location. That's a driver for me. On the other hand, like a Samsung, the price is okay. They have some cheaper phones. But the location's not a big deal. You got a Samsung phone, it's not working. You call Samsung in Korea, you're like, 안녕하세요? Like, yeah, right? And you talk to them and they're like, no problem. We're going to send you a box. It'll be there in 2 weeks. And then after we send you a box in 2 weeks, you take your phone, you put it in the box, you send it back. And after you send it back, we'll take a look at it to make sure you didn't drop it in the toilet. And then we'll send you one back. You should have another phone in like 6 weeks, no problem. And you're like, oh, that's okay. Location's not a big deal to you. I want to be able to go to the Geek Squad and just like, hey man, it's broke. Like, Chris, we got you a new one. I don't want to be like waiting a week or two for some box to come. Like, that's not my thing, right? But the people that buy Samsung, they're okay with that, right? It's not like you can just go in there like fix phone. Like, no. Don't worry, just call in, we'll get you a box. Availability. Those of you that are Apple fans, along comes September, and that's when Steve Jobs used to get there on the stage and like, look at the new thing, and you know, the new phones come out, new products come out. And as the new products come out, the new iPhone 11, I think is coming out, the 10, the 12. The iPhone 12 will be coming out. And imagine September comes, the iPhone 12 comes out, you go over to Apple and you stand in line, you're like, I want the brand new iPhone 12. They're like, sorry, Kira, we're all out right now. We can't get any new iPhone 12s. It's going to take about 3 weeks. You don't say, well, screw you, I'm going to Walmart and I'm going to go get the track phone. I don't need your iPhone. No. You wait. They don't care about availability. They want that iPhone. That's important to them. On the other hand, the Samsung, you go there and you like, hey, I want the Samsung Note because it's got that little pen that comes out and you write notes on it. Like, you know, I'm sorry, Matt, but you know, we don't have any more notes in. Or maybe the only note we have is the one with the higher memory and it's like twice the price. You're just like, you know, and when you get them in, like, I don't know, they could come in 2 weeks. You're like, okay, well, forget it. Just give me the Galaxy 13 or whatever they're at. Availability might be a big deal. You want that phone now, right? You're gonna wait. But the people with the iPhone, like, no, man, I don't want this one. But the other people, like, no, availability is kind of important. The track phone, kind of important, but whatever. I mean, they're just like, I'm looking at the budget price. If it's a track phone, the Mac phone, I don't care. As long as there's something taking place, as long as there's a phone, right? It moves, I just, you know, makes calls. And so when we're looking at this, what we're trying to do is we're trying to find out the drivers. What you will probably do later on when you get into a field, if you're into marketing, you'll have something like this. You'll be looking at, and I'm just going to say, for instance, possibly like pants or shoes or some product, purses. I'm going to say a product of a shirt just for that. And maybe you'll be looking at a shirt with a collar, perhaps a polo shirt, and perhaps a t-shirt. And we'll want to look to see at the drivers. Perhaps we'll look at maybe the price of them, or maybe even the style. Or maybe we're looking at the colors of them. Dark blue, light blue, medium blue. With pocket, without pocket. And then we can start to see, okay, for the collared shirt, for the polo shirt, and for the t-shirt, we can then start to see, wait a minute, people want no pocket, they want the dark blue, they want it made out of cotton. That's what this will be able to show you. What products people are looking for in the area that you're at by doing a simple product test. Okay? And that's kind of what we're looking at. We're now going to look at an example here that I got from our Excel note files, and then we're going to go to our PowerPoint presentation to expand upon that just a little bit more. Okay? Okay, come on, screen share. She's taking her time a little bit today. Somebody give me the thumbs up if we can see that. We see that, Joseph? Okay. Okay. So we're looking at this, and we're looking at cars. We're looking at sedans, sports car, and an SUV. And what we're trying to figure out is what technology do they want? And so here we're looking at a CD player, high quality stereo, cell phone, GPS, movie game player, internet, radar detector, and don't know. Okay? And this is the actual data, observed frequencies of what we found. What we found is looking at sedans, how many people bought sedans and wanted the high quality stereo? 178. How about with the sports car? 58. Right? How many sports cars were there? 196. How many sedans are there? 619. How many wanted the high quality stereo in the SUV? 54 out of 188. You with me? So now we can start to then look at the other products, the other things, and what we then see is how much we observed versus what we expected. And so if we look at how many people right here bought CD players. And so if we look at CD players, 290 people bought CD players out of 1,000. I'm going to say that's roughly 29%. So then what we can say is, so if it's all the same, then 29% of all these people should buy a CD player. So then we can figure out, well, at 29% for sedans, they sold 616. What is 29%? I want to see if they're above 29% or not. So what we do is we calculate what 29% is, and what that actually is this is expected frequencies. That's 178. And see that FO, frequency observed, frequency expected. So this is what we actually found, 178, and what we expected was 178.64. That difference is negative 64. This right here, sports car, what we found was 58. What we expected was 56. So the difference is like 1.6. Over here it's 52. But when we look at high quality stereo, the people in the sedans, what we had was 80. What we expected was 110. That number is below 30. 30 below what we actually expected. So if I take this FO minus FE, that number, that 30, negative 30, and I square that number. So I square 30 and then divide by FE, by that number. I get this number. And that's what that formula is here on the top. FO minus FE squared divided by FE. That is my chi-square statistic. And that tells me a dependency. So it tells me a negative or positive dependency. And like, what does that mean? We're trying to sell cars here. And it tells me, if I put this product in there, will people buy this car? So there's a positive dependency right here. So any of these numbers right here that's above 5, there's something there. So it's telling me that people with, see this sedan right here? High quality stereo, see that number? There's something there with the high quality stereo. Also, right here with the moving game player, there's something there, and there's a dependency there. Now, is it a positive dependency or a negative dependency? What does that mean? One of them means, does it contribute to you buying it, or does it contribute to you not buying the vehicle? So here's the interesting thing. So looking at these, I'm going to turn this off for just a second. When we look at things, like, say for instance, Natalie's out for a little run. She's going jogging, and so she goes out to the house, she gets her little water bottle, gets her little dog with her, and she goes out for a jog, and she's jogging. It's like a 5-mile run. And there's this 7-Eleven on the way going back to her house. And the 7-Eleven's like half a block from her house. So she's like, I'm going to run to the 7-Eleven, and when I get there, I'm going to get a Gatorade, right? Why Gatorade? I don't know. It could be any brand. I mean, it could be vitamin water, whatever. But she's going to get one of those energy drinks. She has it in her mind, I'm getting a Gatorade. Should we get the fruit punch or the traditional one that looks like radiator fluid, whatever it is, right? I'm getting one of those. And all of a sudden she's jogging, and she gets into the store, and she opens up the door, and she looks at the Gatorade there, and the only one that they have is cotton candy. And because there's a cotton candy, she doesn't want that flavor. She's not getting it. She's like, no, it's not my thing. And so there's now a negative dependency because of that flavor of her buying it and not buying it. Okay. Same thing, like imagine you go to buy a shirt and you go into the store and you like the shirt, it's the right color, it has a pocket on it, you know, everything is perfect. And all of a sudden you try it on and you're just like, whoa, wait a minute. It just doesn't quite fit right. And so now there's a negative dependency between the fit and if you buy it or not, right? You go there, you ask your friends like, hey, how does this shirt look? Dude, it makes you look fat. The girl makes you look fat. Like, okay, I'm not buying it. Right? So there could be a negative dependency where you get something else and there's a positive dependency that pushes you to buy it. Oh my God, that shirt looks really good on you. Right? That's why the salespeople talk to you like that. Whoa, you look amazing. Buy 2 of them. But anyway, so positive and negative dependencies. A negative dependency makes it go opposite of what it is. If we're looking at something like Cutter bug spray, and people are like, I love this stuff, I need to wear it here in Hawaii. And so they spray it and they go on a hike and they find out that this bug spray, if you go in the water and it gets into the water, it starts killing the fish. And people that are like sensitive towards the environment, they would say, I like it and it works really good. But people that go hiking, that's the reason why all the fish are dying in this stream. Like, don't wear it. And so they won't wear it. So negative dependency because of that attribute that you are not going to buy this product. And so in marketing, those of you getting into marketing, you're going to live and die by this. You're going to use this all the time when trying to figure out this. So now what I like to do is I'm going to take you to the PowerPoint slide for this. Then I'm going to show you how to run a chi-square. And then after that, if we have time, we'll then talk about all the different tests and kind of like how they all work together. Okay, or how they all, come on, the screen sharing always takes a minute. Select an application to share. She's taking her time. Okay. Can we see that, Garrison? Give me a thumbs up if you can see it. Okay. So here we're going to look at our chi-square 2 categorical tests. Okay. This chapter we're going to learn how, when, and where to use chi-square tests for contingency tables, and how to use the Marsh-Corello procedure. Right? The population mean of a single numerical variable is a t-test. The population proportion of a single characteristic variable is a z-test. The population means for a numerical variable split to groups, categorical, so more than 2 groups, we're looking at an ANOVA. Now what we're going to do is we're going to look at our chi-square, because a chi-square is going to look at more than 2 categorical variables, where we can actually add attributes to them as well. Okay. Contingency table. We're going to learn how to make those when we have these pivot tables, also called the cross calculation table or classification table. We've learned how to make the pivot tables on one of our homework assignments. So we can look at something. Did we look at this already? Somebody help me. Did we do the PowerPoint slides for this? No, I don't think so. I think we did a little bit with right-handed versus left-handed. So we're looking at a right-handed versus left-handed people, right? So we can create a table, and we want to see, you know, is gender and hand preference is related somehow? So we can actually just go, I don't know, into some area and test people, but you know, everywhere's shut down right now. But perhaps if it was open, we can go to a mall and just start asking people, are you right-handed, left-handed, and just get some type of random test. And so what we're trying to find out, The proportion of females who are left-handed is equal to the proportion of males who are left-handed. So what we're trying to say is it's the same. Alternative hypothesis says no, there's a difference based on gender. And so we can check this. So again, that's our frequency observed minus frequency expected divided by frequency expected. Do we have to calculate this stuff out? No. Now, if we're looking at the amount to calculate the amount that we expect, remember again, we had 120 females, 12 were left-handed, and 180 males, 12 were left-handed. So we had 12 females left-handed, 24 males left-handed, which gives us 36 based out of 300, which tells us 12%. And so as shown you before, so then we can start to calculate how many we expect based off of those percentages, right? How many left-handed people? 36. How many females are there? 120, right? 12% of that, 14. So what is implied if there's a large difference between the expected and observed? What that's telling us is that there's a dependency between whatever it is that we're testing. There's a huge difference here when we say dependency, right? And probability. Even though we're basing it off of a probability, right? The probability of the likelihood of something taking place, the likelihood of this being dependent. Dependent means that if A happens, B happens. If I say this, so imagine this, right? Let's wake up here a little bit. So imagine Jasmine decides, wait a minute, I really like baking stuff. So I'm going to open up a bakery store. And so Jasmine opens up a bakery store, and lo and behold, she's making cupcakes. She thought I was going to say brownies. No, Jasmine, you're not making brownies. She's making cupcakes, cookies, pies, cakes, stuff like that. And all of a sudden, the price of flour and the price of sugar goes up. What do you think that does to the price of her products? Help me here, Hannah. If the price of flour and sugar goes up, what do you think the price of her products, what's going to happen?
It'll go up as well.
Why?
Because it'll be more expensive to produce.
Is that a teddy bear? I like that. Let me see it. That's cool, right on. But you're absolutely right. So her products are actually dependent upon flour and sugar. So if the price of flour and sugar go up, the price of her products go up. So dependency means that if one thing happens, the other one happens. If the price of oil goes up, the price of gas goes up, because oil is dependent, or gas is dependent upon oil. And so when we're looking at this chi-square, what we're saying that if we reject our null hypothesis, we're saying that there's a dependency between these two things. So here we actually have our chi-square value, which is 0.38, that's our p-value. Now, again, for all of our tests, if our p-value is below our level of significance, we can reject our null hypothesis. So in this case, our p-value is 0.38, and our level of significance was 0.5. So there's insufficient evidence to reject our null hypothesis. There's absolutely no difference between gender. There's no difference between gender and hand preference. There's insufficient evidence to reject the null. Okay? And that's what we're looking at, observed frequency and expected frequency. And we're kind of comparing those to see, wait a minute, is it higher than we think? So here's another one where we have a university is thinking about switching to trimesters. So imagine this, a university is thinking on switching to online classes, Zoom classes. I'm just going to change that up just to make it real here. And so the administrators are in favor of that. Why? So looking at the administrators, the ones in favor, 63. The ones that oppose it, 37. Why? Because if they do teach it online, they don't have to pay for air conditioning in the classrooms. They don't have to, you don't use the toilets, the bathrooms, none of that kind of stuff. It's cheaper for them to operate. Why wouldn't they do it? Bigger classroom sizes, just, you know, say, hey, instead of having 10 classes, because we can only fit 40 people in a class, we're now going to make 100 people in one class. So the administrators, of course, it makes more sense because less teachers, cheaper. So the administrators like that. The students, you know, in favor, 20, but 30 of them are like, hey, no, wait a minute. I like going to school, man. I didn't before, but now that it's taken away from me, what's that? You don't love something till it leaves you, right? And then all of a sudden now they're just like, hey, wait a minute. I like going to school now. I oppose it. But 20 are in favor. The faculty, some of them are like, hey, wait a minute. So if I want to travel, imagine you could travel, even though it's a 15-day whatever, I can go out to Paris for 3 months and teach from Paris in 3 months. So I'm on quarantine for 14 days. I don't care. Right? I can teach for 3 months. All I have to do is lecture for a little bit of just travel. So the faculty, 37 out of 13 want to do this. And so if we want to see, is there evidence that the different groups have different agendas? Do they all feel the same, or is there some difference between the people? So we can test this. So we write a hypothesis that, you know, the administrators, the students, and the faculty, they all feel the same, right? Our alternative is like, no, there's a dependency between what group you are and how you feel about this. And so when we look at if we look at that tab right there that says data, the blue one, and it says level of significance 01. So it's not an 05, it's 01, so 99% confidence level. The number of rows and columns, degrees of freedom. If we go down to the bottom, we have critical value, chi-square statistic, and right below that we have a p-value. That p-value, so we have our level of significance up there and our p-value. Our p-value is 0.001. Our level of significance is 0.01. So because our p-value is below our level of significance, and we see it in the box right below that, it says reject the null hypothesis. There's a difference. Now with our ANOVA, it just tells us that one of them is different. How do we know which one's different? We use our Tukey-Kramer. Right, we use our Tukey-Kramer. For the chi-square, we're going to use our Marshmallow. So it is the Tukey-Kramer for the chi-square. It's going to tell us which one's different. But here's the issue. The Marshmallow is not that powerful. So it's only going to do like a 2x2 or something like that. If you want to know the difference when you have larger samples, more variables, we have to look at percentages of rows and columns. Okay, so this is the Marshmallow, and we're looking at the absolute value compared to the critical range. Okay, so if do we see that? So our critical range, so if our absolute value is greater than our critical range, then there's a difference. So if our value is higher than that critical value, there's a difference, right? That group is different. Okay. So when we're looking at, when we have more than a couple variables, right? When we have more than 2 or 3 variables, when our chi-square starts to get a little bit larger, our Marshmallow becomes, instead of using the Marshmallow, we're going to use our percentages of rows and columns. So hypothesis is the same. Categorical variables are independent. So our null is the variables are independent. Our alternative is there's a dependency. Again, same thing. Our observed frequency, right here we're looking at survey of investors and the attitude and the age groups, like how much, you know, would they invest? Here's their attitudes, you know, out of 500 people. So how many of them are in favor or not in favor, looking at a bearish, neutral, and bullish markets? how many of them would invest based off of somebody 18 to 34, 35 to 44. And so we're looking at these and see, is there a difference between who invests and their age, right? The attitude and age. And so we can test this. And we find out what the observed ones are and what the expected are. Then we can get our chi-square statistic. And based off of our chi-square statistic, if it's below our level of significance, we can reject our null and say there's a difference. But right here, our p-value is 0.99. Our p-value should be below 0.05, 0.05. So how confident are we that there's difference? We're like 1% confident. There is no difference at all. Age does not affect when you invest. Probably has more to do with how much money you're making, but age is not a significant predictor. Okay? Age is not a significant predictor. So when we look at our FO minus FE, do we see those numbers right there? Where it's 15 and 6? If there was something, if there is something that was different, that any number is very different. Any 5 is showing that there's a difference, but anything above 10 is significantly different. So in this case, we would say that anyone 55 and older, they do have some issues with the neutral and the bullish market, right? They have a better view towards it than the other ones, okay? That's kind of the chapter summary. Let's now look at how we create this. Okay? Why do we need to do that? Because we actually have homework. Okay? Sorry about that. Exit full screen. Do you have any questions on this so far? Somebody asked me. Questions? Why would we use this stuff? Some of our exercises will use this. Okay. I'm loading it right now, and so she's taking her time. So I'm launching PHStat right now, so give me just a second. Okay, so here we go. Fund, share. So Max, give me a thumbs up if you can see this. Okay. Or yeah, Joseph, You turned your camera off on me. So let's now see if we can create some type of chi-square thing. So I'm not sure if you guys remember how to make a pivot table. It's going to be highly useful for you, especially when you get to finance, because they are going to do this quite a bit. So I'm going to refresh your memory so we can make this one of those tabulation tables, cross tabulation tables, where we can do all kinds of probabilities, all that stuff from here. Okay. Highlight it all, insert, pivot table. Okay. So again, columns and rows are categorical data and values are numerical. So I can have like types of bonds, intermediate, government, short term. I can also have like risk. What types of bonds we have, what type of risk that we have that we're playing with. So we're looking at different bonds and we're looking at our different risks. And then what I could do if I wanted to is have 5-year tax returns. So actually how much money you made. And so you can see what I drug to which area. You can see how much money people actually make based off of how much risk is involved. So we can look at this even from a probability things of average risk with an intermediate government bond, average risk with a short-term bond, right? Sorry, above average. And then we can look at average risk for both of those, below average risk, right? So above average risk is high risk, average, and low. So how risky they were, and was it a short-term bond or just an intermediate bond? And we can actually see how much money people made. And we can see, is there a dependency between risk and reward? Because people always say that. And so we can actually look at the data. What's the data showing us? Is there a dependency between the type of bonds you make, that you buy, short-term, long-term? And is there also a dependency between the risk and how much money is taking place? If you're in finance, you want to be able to talk to your people about this, or your clients. So we're going to make a chi-square test to see if there is an issue with this. Here's my chi-square. I launched this. We'll do that again. Can you see this, Caitlin? My screen? Okay. Do our add-ins. Oops. Design. Okay, why does it keep on doing the design tools? Let me launch that again. Nope. That's not the one I want. Okay, I'm just going to have to shut down the water one. Water chi-square, shut down. Don't save. Page done. Okay, there we go. Can we still see that there, Caitlin? Okay, so now I'm going to go to my PHStat, and I'm going to go to my multiple sample tests, and chi-square. I'll leave it there for a second for those of you that are trying to find that, but it's under multiple sample tests, same place with the ANOVA. I'm going to click on that. Do we see this right here? Number of rows and columns. So level of significance, 0.05, or you can put 0.5. Number of rows. So rows go this way, columns go up and down. Columns hold up the roof, so Roman columns. So how many columns do we have? How many rows do we have? Somebody help me. Is that 3 and 2? Okay. So do we see this new thing that was just put out there? Can we see that, Wilfred? Give me a who? There we go. All right. So now we can compare these. You're like, well, do we see how there's nothing in here? You know what we're going to do? We're going to go to this, and don't highlight it from this end. Highlight it from the bottom. So bottoms up, right? So we're going to highlight this. The reason why you don't want to highlight it from the top is because they have a drop-down menu. So if you start off at risk, you try and it starts dragging stuff all over and you end up with a mess. So start from the bottom and go up to the top. Copy that. I'm going to take the chi-square and I'm going to paste it there in the observed frequencies. Now, put that in the right place? Let's try that again. Okay. From here, sorry, to there. From here to there and copy. I went too high. I just want to go to where risk is, right there, right? And I'm going to go over here. There. And paste. Okay. And so this is our chi-square now. Now we can start looking to see, is there a difference? Looking at short-term bonds and long-term bonds. And so any number, so right here it says, do not reject the null hypothesis. That means there's no difference. But if there was a difference, we would go to FO minus FE, and any number above 5 shows us that there's some difference. Anything above 10, significantly different. Now, wow, everybody's got their camera turned on. So Melissa, are you wondering why 5 and 10? Earth to Melissa. Maybe Melissa's not there. Okay, how about you, Kelly? Are you there, Kelly? Hello, Kelly? Okay. How about you, Nicole? Is my mic turned off? Ashley, is my mic turned off? Can you hear me?
I can hear you.
Okay. I wonder what happened to the other people. I wonder what's up with them. Okay. So, how about you, Brooke? Are you wondering why I said FO minus FE if the number is above 5 or 10?
Maybe.
There we go. A definite maybe. All right. We're getting somewhere. Right. So what it is each one of those numbers is the chi-square test. All those numbers, FO minus FE squared divided by FE, see those numbers right there? That is basically where you get your p-value from. And based off of those numbers actually give us a p-value of what that value is. And so a number that's above 5 gives us a p-value that is somewhere around 5 or somewhere below 0.05. A chi-square value of 10 gives us a p-value of somewhere around 0.01. And so if we look at this chi-square chart right here, and you look at the numbers, that's where it actually tells you where those values are. And so, see that right there? That chi-square value of 5.991, that value right there is below 0.05. So it's telling us that a chi-square value of 5 is right around roughly the p-value of 0.05. So if you see a chi-square value here and it's 5 or higher, you'd be able to say, oh, there's a dependency there. If there's a chi-square value of 10, definite dependency there. And then you want to go up to the FO minus FE and see if it's a positive dependency or if it's a negative dependency. Because sometimes things would create you to not want to buy something. Like imagine you're looking at a pair of shoes and you're like, do I want to buy them or not? And you like them, you love the look of the shoe, the fit is good, then you find out that you want leather shoes. They look like leather, but they're not really leather. And you're like, no, I don't want them because my feet really sweat really bad in these plastic shoes, so I'm not going to buy it because it's plastic. And so then you would see a negative dependency. Because of the materials, you don't want to buy it. And that's our positive and negative dependencies. And that's kind of our chi-square. And so when we're writing this up, if we look at our, if we go back to our website and go to our resources, that same document that shows you how to write up an ANOVA, a t-test, and a z-test, there's always something there. That also, there's also something there that shows us how to use that template to write it up for a chi-square. Okay. So now what I'm going to do is part of me, and so those of you that know me know, those that don't, but part of me is, although I'm very mathematically based, which most people get blown away because until I tell them that, they would have no clue. And I'm very scientific based, but for the most part, I have this huge part of me that's also very creative, artistic. I say autistic or artistic? Artistic, right? And so there's this huge part of me that's very artistic. And so I'm able to think outside of the box, which a lot of people can't. So I like coming up with these examples that would allow you to also go along with this journey, because at the end result, what I want is for you to be able to see this and understand exactly what we're doing here. That way, when you get into a job or something, you get it. And when you're in another class and somebody says something, you can totally understand it and you can see how all these things work together. And so I love that. So I just had a great discussion with a student over the weekend who took my class, oh my God, 9 years ago. He actually founded a club here, and I remember him having to take my class 3 times to get through it. He had a really difficult time, and then when he finally got through it, he's like, I'm never using this stuff ever again. And it's funny because I got a wonderful email from him. He is now an analyst at Wells Fargo Bank. And so I was just like, what happened, man? I thought you weren't ever using it. He's like, I know. He started laughing. Like, I can't believe it, but I really like this stuff now. So now he's embracing it. But what I want to do is I want to take you guys on a journey because I want you to see this. So imagine, I tell you guys, hey, wait a minute, this stay-at-home order is over. Like, it's been a rough semester. Like, Chris is throwing a little party, right? So we're all going to have a little party over at Kahala Mandarin Hotel, right? Chips, dips, a soiree, right? And so everybody's going to show up, and all of a sudden, as soon as we get on the bus, we're getting ready. Everybody's like, my favorite 7-Up. I'm going to drink like a whole bunch of them. Someone else bought their 7-Up bong to drink a lot of 7-Up in one place, right? And so we're getting ready for that huge party, and all of a sudden, these 2 men in black walk into the bus. And they're real serious looking, so we all sit there like, okay, what's going on? They tell the bus driver, get off the bus. The bus driver leaves. They drive us like a block down. They stop. They lock the doors. Helicopter lands. Somebody comes in and says, you know, Earth is going to be hit by a giant meteor in about a year. And we know for sure that it's going to destroy Earth and everybody on it is going to die. What we need to do is we need to send some people out because we have to start to repopulate other planets. And we need to make sure that this planet is viable for us, a Goldilocks planet, R327 or whatever. And so we're going to actually send you guys through a black hole. You guys have been selected because of your knowledge of statistics and other stuff too. We've checked you guys' DNA and you guys are a perfect mix for it. So everybody here, you have just been volunteered to go to this planet. And all of a sudden, Brooke is like, hey, can I call my parents or can I whatever? And aren't they going to miss us? And they're like, hey, Brooke, well, you know what? We've already got a cover story. This bus is going to have an accident, catch on fire, burn up, and everybody in it, we're going to say it's gone. And you're like, whoa. And so nobody can call anybody. And all of a sudden, Nicole's like, hey, I'm not okay with this. I don't want to go. No problem. Just leave her on the bus when it burns up. Well, hey, wait. I was just kidding about that. Well, yeah. And so imagine we all go down to Cape Canaveral. You know, they put us on the ship. They're going to send us through this black hole. They give us a shot. You'll be sleeping for about a month. You'll wake up, and you'll be landing in orbit in this new Goldilocks planet. We're going to call it Earth 2. And so we actually get there. We land. And we have to be careful because on Earth 2, we don't know. Out here, we have a spider bite you, right? A black widow, you can die over there. There's all kinds of stuff. We have no idea about anything, so we have to be super cautious. A little bug comes up to us. No, no, no. Do not get close. Don't even crush it because we have some bugs that they put out a gas. They smell bad, but maybe this has a gas that puts out that kills us. We have no idea. Matter of fact, although we think that the atmosphere is okay, do we really know? And so we get there and we land and we're like, well, you know, should we go outside? And Asia's like, you know, I don't know. Like, how do we know if it's safe? Edna's like, I got this. So we know Earth, oxygen's O2. And new Earth, you think our oxygen is the same as that one. So where we're at. So we can measure it. So we have our level of significance and our p-value. And if our p-value is below the level of significance, then that means that new Earth and old Earth, the oxygen is not the same. And that means we can't breathe that stuff. So we're going to have to be walking around with tanks forever. Like, and how long will that last? So imagine we go out there and our p-value is 0.99. There's insufficient evidence to reject the null hypothesis. That means that new Earth and old Earth, we have the same oxygen. We should be okay. Right? How confident are we of that? At 99%. Right? So, okay, we're good with that. So we go outside and we start breathing. We're like, okay, this is cool. And so we're walking along the path and we already have caution, like be careful. An animal comes up, it could kill us. We don't know if there's dinosaurs here, velociraptors, nothing. So we're okay. So we start walking to take a look at our new environment. And so we're walking along the path and we see this pool of liquid. And right away, Alex is like, hey, look, there's water. Like, we don't know what that is. Hell, it could be acid or some chemical that we have no idea. We need to test that to see if it's water. And don't get too clear, because on Earth we have alligators. Here we have no idea what it is. Now there could be something that we can't even see that pops out of the water and eats us just because photons don't bounce off of it, so we can't even see. So be careful when you get close to that water, even to get a sample. So we go, we get a sample, and here on Earth, so the first test we did was that t-test, right? So here on Earth, we're looking at water. Is H2O. 1 part hydrogen, 2 parts oxygen. So we're saying the proportion of hydrogen and oxygen on Earth in the liquid and the proportion of hydrogen and oxygen on this planet is the same. And it doesn't have anything else in it, like arsenic or any of the rest of the stuff. No. Water, it's not the same. It's not water. We run our test. There's significant evidence to reject that. Guess what? This ain't water. We better put a sign there that says, do not drink. This is not water. Who knows what it is, but it ain't water. And so then we move on and we go to another pond or another giant thing of liquid that we call ponds here on Earth. And we run a test. Insufficient evidence to reject the null hypothesis. Guess what? The proportion of H2O from Earth in water and the proportion of H2O in this pool, or this pond, says that this is water. We found some water. Good. Now we're okay as far as drinking water. Right? We start setting up a little village right here next to the pond. We got some water. We got a bunch of seeds and stuff to start growing some plants. It's a good thing. We start thinking like, hey, well, we're going to be here for a while. There's no way back, right? There's no way we can get back to Earth. It's over, right? Now we either set up some stuff, we get it going, and if it's going good enough, they'll send some more people here. They have other groups that they send to other planets, but hopefully they choose ours, or maybe ours is one of the places. So we start looking at it, okay, well, what plants do we grow? Because what we understand that some plants will grow, but if it's going to take us 8 years to get a peach, we don't want to grow that. We're going to use a lot of water. It's going to take a lot of effort. If corn takes 1 month to grow, then guess what? That's what we're growing. So what we're going to look at is the speed on which these plants are growing. We're going to say, oh, they're all going to grow the same. We have roughly 200 different plants that we're going to try to grow. And so we're going to say they're all going to grow the same. So not all means the average amount of time that it takes to grow are equal. Okay. We test them to see which ones are going to grow the quickest. We're able to reject that null hypothesis, and we've planted like 500 different plants, 200 different plants. Doesn't matter what the number is, but we plant a whole bunch of different plants, and now we find out that one of them's different. The interesting thing is that the ANOVA doesn't tell us which one's different. It just tells us one of them's different. Now what we're going to do is we're going to use our Tukey-Kramer, and it's going to tell us which plants are significantly different. So we start testing them, and we find out, hey, wait a minute. Okay, the peas, the corns, these plants are growing really quick. These are the ones that we should grow. Of course, we need to check our assumptions for our t-test. We need to check our assumptions for our ANOVA, chi-square, and make sure that we have enough samples and stuff. But we now know which plants we can grow. And then we start looking, hey, wait a minute, we have some stuff that we call here on Earth fish, or aquatic life. We have many different types. And so we see some of these waterways, and we see some ponds and aquifers and whatever, and we notice that they have some sediments in it, but we can filter it out and drink it, but is it safe for the fish? So what we want to do is we want to put our fish in these waters to see which ones are thriving. And so we actually create this chi-square, right? And so let me show you the chi-square that we actually create, and let's take a look at what it tells us. Whole bunch of people dropping off. We running out of time or something? Let me share this. Okay. So here we are looking at this. Can you give me a thumbs up, hand up? You see this? Okay. So here we're looking at, we have a lake, a stream, and an aquifer. And we're looking at the different levels of stuff we want to have in here. And we put our fish in here, and we're looking at the survival rate of how many of them are actually surviving with these different levels of contaminants in it. And so what we find here is the amount of heavy metals, salt levels, sediment, sunscreen. I don't know how it gets sunscreen in there, but you know, we're from Hawaii, right? Somebody's swimming in the water and they're not telling us. Minerals, algae, bacteria. And based off of these different sediment amounts, we're now able to see how many fish are actually surviving within these, within the lake, the stream, and the aquifer. And we find here that when we do our test, that there's a dependency, see right here with the salt levels? And see that negative dependency? That means that high salt levels are actually creating our fish to die. So if we want to optimize this, we better take some of the salt out of there. So less are surviving than we thought, and it has to do with these high salt levels. Also with the minerals. We start looking at the minerals here. And see the minerals, positive numbers, so they like the minerals. Our fish are actually surviving with the high minerals. When we start looking at the bacteria, and the bacteria, negative number, is actually causing our fish to die. And so we can start looking at these numbers here to see what is helping and what's not and how we can fix this. And that's what this is telling us, right? So now we can go and we can start managing our waterways. So here's the interesting question that I think is great. Do we actually do this already? Do we do this right now, Javon? Do we actually go in and test our waterways to see if they're drinkable, to see if it's really H2O anymore?
Yes, I hope so.
We do. Do we actually look at the survival rate of fish and stuff like that? Yeah, we do this right now on Earth all the time. Every single one of these tests where we're constantly testing the air and the oxygen, and or is the oxygen levels or falling down? Do we have other chemicals in here, chemtrails, or whatever it is that people are looking at, right? Too much aluminum or whatever it is, sulfuric dioxide in the air. We're testing these all the time. And so even though I took us on this hypothetical journey where we're using these tests in order to control our environment, we actually really do that on Earth currently. Okay? So all these tests, I just want you to see that they're highly useful, they're very powerful, and they use them in multiple different areas, not just to see if a marketing plan is better than another marketing plan. No, that is not the totality of them. They're pretty powerful tests. Okay, and I just kind of wanted to bring that to you guys so you can actually see some of the capacity or the capabilities of the stuff that we're learning. Pretty powerful stuff. Now tomorrow, I hope that everybody logs in early, stays as late as they can, because we're going to do regression, and this is the one that is going to wake you up. So I just kind of want to do a quick thing of where we're at to see how much of us are learning what. Where are we at, Alex? Are you getting this? Okay. How about you, Aisha? Are you, I don't want to wake you up there, but are you getting some of this? Maybe she's gonna wait for that video. Moana's laughing. Come on, girl. You're like, Chris, I don't think she hears you.